Okay. So last time we dispersed at a place and I said you should read up the inversions. So have you guys seen it?
Yes, I read it.
Okay, what are inversions? Yeah, Ridhima?
Yeah, so the I mean it's a permutation. I mean it's a mapping where uh, it's a mapping where each permutation is uh, uh, mapped. Okay, just a minute. I forgot the. Uh,
Agilan?
Yes, ma'am.
What are inversions?
No, ma'am, I didn't look it up.
You're not audible. Sorry, I can't.
I didn't look it up. I'm sorry.
Okay. Okay, so since Ridhiman is also not so well versed with it, let's leave it to the next class. And today we'll start with the new topic. Okay, I'll try not
I
to
think
mention the inversion. Huh?
I think it will be better if you leave it for the next class. I mean after the quiz. So
You should not have said this, Ridhiman, since you said you have already read it. It should not have made a difference to you.
okay, anyway.
But anyway, so we'll see that today. Then I'll not mention inversions and try to do it without that term as it is. So the main things which we have to see today are descents. And if at all you people have had any exposure to algebra before, then alternating permutations and Euler number. Okay. So what we say is that first of all, when we take a permutation in Gn, so Gn, remember, was the set of permutations on n elements 1 up to n. Okay.
Yes.
So if this permutation is written as a word W1, W2, Wn, so already you know that all these elements are distinct. They're different from each other, right? Because you're taking a permutation on a set. Okay.
Yes, ma'am.
So these Wi's are nothing but elements between 1 to n, isn't it?
Yes.
So in particular, they are comparable. So either two of them satisfy the inequality less than or inequality greater than. Correct?
Yes.
So if at any I you're standing and you see Wi, so compare Wi with its next element. If Wi happens to be larger than its next element, then you say that I is a descent. And if Wi is smaller than Wi plus 1, you say that I is an ascent.
Ma'am, I remember what the inversion is. So it is if Wi is greater than Wj and I is less than j, we call it an inversion. Actually, I was confused
Okay,
with the inversion table thing.
no problem.
Yeah.
So standing at any location, you compare that particular element with its next element. So if let's say here is where I'm seeing, I compare it with just this next one here. Okay. And if this one is bigger, I call it a descent. So every time this is the point of reference. This is the ith location. Okay. I don't know if this looks like an eye. So this is the ith location. You compare it with the next location. If this element is happens to be larger than this, you call the ith location to be a descent. If this element is smaller than this, you say that ith, the number I is an ascent because it is giving a smaller value. Okay. Now with this, given a permutation in this format, you can collect all the descents of this permutation, which means you stand at 1 and you compare the W1 with W2. Either W1 is going to be bigger than W2 or W1 is going to be smaller than W2, right? So if W1 is bigger than W2, you are going to say that 1 is a descent, right?
Yes.
Therefore, I is in this, 1 is a descent of W. Similarly, you now come to 2 and you compare it. Then for the 2, you will have to compare W2 with W3. If W2 also happens to be larger than W3, then what does that say? That 2 is also a descent. So this way you can collect all the descents of the permutation W. And that set is called DW. So this DW is the set of all the descents, okay, of this particular permutation W. So clearly DW cannot have the element small n. Why? Because you compare elements up till here, because you have to compare the element with its next element. If you want to compare n, what will you compare it with? There is no wn plus 1 here. You have written it as a word now, right? So if it's a word of length n, n happens to be the last element in the string. Therefore, the last comparison that can happen is at the level of wn minus 1. All right. So dw is a subset of this set n minus 1. Now, if you take any other subset of n minus 1, you take any such set S, then you define alpha S to be alpha S to be the number of permutations for which the descent set is a subset of this set S. Okay, so given any W, dW is fixed, first of all. That is what you have to see. Okay, now you're doing the other way around. You're saying that I start with any set S of n minus 1. And now I want to see all those permutations whose descent set, which is this set, is a subset of this set. Okay.
Yes, ma'am.
Similarly, this is the notation. So alpha S is the notation for this number. And for some for some times when you are not so careful, or rather when you do not want to write too much here, you put this n also here, so that you are saying that you are taking permutations from a set on permutations of a set with n elements, and the set you're considering right now is this set. Okay, so this is a shorthand notation for this huge thing. So this entire thing would vanish with one n here. And similarly, you define another parameter beta ns or beta s, which gives you the number of permutations whose descent set is exactly equal to s. Okay.
Okay.
So with these two parameters, alpha s and beta s, can you give me a relation between these two?
Beta S will be smaller, lesser than alpha S.
Okay. More?
For each
Okay.
subset of S, The sum of the betas will be the alpha.
Which sum?
The sum of all the beta of for each of the subset.
So basically you keep on varying the S here in your beta S, and that's how you collect all these beta S's here for your alpha S, right?
So can you repeat it, ma'am?
So we said that alpha S is nothing but the number of those permutations whose descent set is a subset of S, whereas beta S is the number of those permutations whose descent set is exactly equal to S. Okay,
Yes, ma'am.
so which first observation is perfectly great, which is that the number of permutations whose descent set is exactly equal to S has to be less than equal to the number of permutations whose descent set is a subset of S. Because if this set S happens to be the whole set, let's say, like just for the visual purposes, this is very, like, these are very few permutations satisfy this, whereas many permutations will come into this set. So now if you want to express alpha S in terms of beta S, what Ridhiman is saying is that instead of looking at this set, why don't you rewrite this set as the number W in Gn such that dW, so collect all the subsets of S, okay? Let's say S1, S2, SR, are many subsets are there of S, basically 2 raised to mod S are there. And then for each of these sets, you collect this particular number. So dW equals to S1, dW equals to S2, dW equals to S3, and so on. So this way you will have different beta S.
Yes, ma'am.
And when you collect all of these beta S's, then you would have got the number alpha S.
Yes, ma'am.
So that's what he's saying, and that's what we have written. So alpha S is nothing but summation of beta S primes, where S prime is a subset of S. Okay.
Yes, ma'am.
Sorry. So if you people remember, some time back we did something called a combinatorial reciprocity, where we wrote the n multi-choose k in terms of n choose k with some sort of signed notation, right? Do you remember?
Yes,
So
ma'am.
just like that, there are more equations, and one of them we'll record now without a proof. We will, if time permits, we'll see this later in the course, which says that once you have alpha S to be this summation, beta S can be rewritten in this fashion, that beta S happens to be the summation, signed summation of alpha t, t subset of S, and this sign is coming from mod of S minus t, cardinality of the set S minus t. So this is actually set minus, though I have written S minus t, it's a set minus. So t is a subset of S. Okay, just how we did here, you run it over all subsets of S, and sort of like inclusion exclusion principle, that whenever this number is odd, you subtract it, whenever this number is even, you add it. Okay, because S remains fixed. So this we will see later if at all we get time. But as of now, just remember this and this will come handy just in a while. So one exercise for you people is that if you take S to be the set S1, S2, Sk, clearly subset of n minus 1 with Si is less than Si plus 1, which means it's written in an increasing order. Okay? Then the number alpha is this parameter which we defined here to be the number of descents for which the number of permutations for which the descent set is a subset of S, turns out to be the multinomial coefficient n choose S1, S2 minus S1, S3 minus S2, and so on till n minus Sk. Okay, so this is an exercise which you should do. It will pop up in the next assignment. Or right now we assume this and proceed further and do an example. So for n greater than equal to 9, if I ask you to compute beta n of 3, 8. So 3, 8 is already a set which is written in an increasing fashion, right? So I can rewrite my beta n of 3, 8 using this particular equation as beta n of 3, 8 to be summation of minus 1 raised to, oops, this is a bracket, it's a bar, not a bracket. So cardinality of S minus T, alpha T, where summation runs over all subsets of S. Here S is the set 3, 8, right? So all possible subsets of T are the empty set, singletons 3 or 8, or the full set 3, 8, right? Is that
Yes,
right? I can't hear any voices.
Yes, ma'am.
yes, ma'am.
Okay. So you put that beta n of 3, 8 happens to be minus 1 raised to 2. So mod S minus empty set. So this is the whole set S, therefore the cardinality 2 and alpha of 5. And so on, minus 1 raised to 1 alpha of 3, minus 1 raised to 1 alpha of 8, and minus 1 raised to 0 alpha of 3, 8. You understand this equation, right? I don't have to
Yes, ma'am.
Yes.
elaborate it. So alpha of empty set is always 1. So this is 1. This is n choose 3 from this formula. Similarly, this is going to be n choose 8, and this is going to be n choose 3, which is the first one, as an n multi choose 3, comma 8 minus 3, right? S2 minus S1, S3 minus S2, and last one is n minus Sk. So n, first element is 3, second is S2 minus S1, so 8 minus 5, 3, and then last element is n minus Sk, so n minus 8. This gives you the number of descents, number of permutations on n elements for any n greater than equal to 9 whose descent set is equal to the set 3, 8. Okay, you see how elegantly we have come down to this number. Otherwise, I don't know, we would have to maybe possibly sit down and write all the possible permutations and then compute every permutation's descent set and then compare with the set S. But nice thing being done. Now, another question which pops in our head is that here we dealt with S to be any subset and we compared it with the descent set. What happens if the descent set itself has some special properties? So when you're working with integers, what are the like the most natural sort of patterns which you see? Like for instance, let me ask this, most of you might have done, or if not done, please try. Or but maybe I try, don't try, your wish. So when you're in a hurry and you are taking stairs, do you skip stairs?
Yes,
Yes.
Yes.
How many?
1 or 2.
But do you do that with your left foot? You would skip one stair, and with your right foot you would skip two stairs.
No.
No, mostly the same number.
It's the same number, because otherwise your body will not find a balance and you'll topple and come down, and then you'll be further late. So just like that, if let's say here also the sets have this sort of a property that you take one, leave one, take one, leave one, take one, leave one, then what really happens? And especially with the descents, where descents have this property that if at all you if the next number is smaller, this is a descent, therefore this comes in the set. And if it is not coming in the set, which means the next element is actually smaller, right? So when you're comparing elements here, these are the only two possibilities for the inequalities. You cannot have Wi to be equal to Wi plus 1 or Wj for that matter. So either this is satisfied or this is satisfied. So elements which are not in the descent set are automatically the elements that are ascents. Isn't that so?
Yes, no.
Yes.
So we take this one notch up and notice. Oh, so I've already written all this here. So if dw happens to be the set of all the odd integers from the set of n minus 1, first n minus 1 integers, or it happens to be the set of all the even integers from this set, then what does it really say? So for instance, let's say if you fix n to be 8 and dw to be coming of this type, then it's the set 1, 3, 5, 7. So 1 belongs to dw implies that w1 is bigger than w2, right?
Right.
Similarly, if 3 belongs to dw, I know that w3 is bigger than w4.
Yes.
Yes.
Similarly, if 5 is there, w5 is bigger than w6 and w7 is bigger than w8, right?
Right.
Also, 2 is not there. 2 is not in dw. So, w2 is smaller than w3. Because w2 cannot be equal to w3. w2 is not greater than w3, because if it was, then 2 would have been in dw.
Yes. So W2 is less than
So
W3.
w2 is less than w3. Similarly, w4 is, oh, I have made a mistake here. This should have been w4 less than w5. Okay, for the same reasoning that 4 is not in dw, which means 4 is an ascent. Therefore, w4 is less than w5. Similarly, w6 is less than w7, right?
Yes.
Now you put all of these things together. So w1 was bigger than w2. Remember, w1 bigger than w2.
Yes.
Then w2 less than w3. Then w3 bigger than w4. Then w4 less than w5. w5 bigger than W6 and so on. So putting this in one line, I get that W1 is bigger than W2, less than W3, bigger than W4, less than W5, bigger than W6 and so on. So this is a sequence of numbers arranged in a zigzag pattern. The less than and greater than symbols appear alternatively. Not even a single time it would happen that the two less thans appear simultaneously or two greater thans appear simultaneously. Okay, so it's a proper zigzag with one less than, then followed by a one greater than, followed by another less than, and so on. Okay, so if I want to write it in a pictorial way, I would write W1 being bigger. I have put W1 on a higher level and then W2 on a lower level. Okay, so this way it's like W1, you come down to W2 because W2 is smaller, and then W3 is again higher, then W4 is smaller, then W5 is higher, then W6 is smaller, W7 higher, W8 smaller. Okay, so this is another way of saying this zigzag is that it's a sequence of downs and ups. The arrows up, down arrows with down coming first and up coming later. Okay.
Yes, ma'am.
So when you have a sequence which represents a zigzag of the form down first and up later, such a permutation is called an alternating permutation. Okay.
Yes, sir.
So for example, if I write, so okay, another word of caution here is that this in no way I am saying that you would be comparing these elements or you would be comparing these elements. I am comparing them in this pattern. All right. The pattern in which they appear in your permutation. There are no arrows here in this horizontal line. So I am not comparing those elements. There is no arrow here in this horizontal line either. So I'm not comparing these at all. I am only comparing this with this. I am, for that instance, not comparing this with this also. No. This comparison goes only with this. This comparison goes only with this. This with this, and so on. Okay.
Yes, ma'am.
So one example of alternating permutation is this. You take 2, 1. So 2 is bigger than 1. So it's a, let me. So from 2, you go down. From 1, 1 is smaller than 4. So from 1, you go up. 4 is bigger than 3, which means you went down. 3 is smaller than 6, so you went up. 6 is larger than 5, so you went down. So you see, you have actually made a alternating path with of zigzags with down first. Okay. Okay.
Yes, ma'am.
Yes.
So Riddhiman is from CS, but Agilan, you are from maths, right?
Yes, ma'am.
So you might get confused in this with the normal notation of alternating permutations, which we see in our algebra.
Yes, ma'am. That is what I was thinking about. Is this
So
related to that?
yeah, it's completely related to that. They are indeed the same. However,
Okay.
what you define there as the alternating permutation is exactly opposite of this.
Oh, I see. So,
Okay. So
yes,
the
ma'am.
alternating permutation which you see in abstract algebra is a up first, down later sequence. or if you would see in combinatorics, if I don't know if you people are familiar with discrete Morse theory.
No, ma'am.
Okay. Acyclic matchings.
No, ma'am.
Ridhiban, you have seen acyclic matchings?
No, no.
Okay, check it. So, okay, so the notation wise, stick to what we have defined our alternating permutation to be. Okay, this will be opposite of what is defined in abstract algebra or in other combinatorial books. But since I'm keeping this book fixed, I have kept this notation also fixed. So
Okay.
if I talk about this 3142 in G4, can you tell me what kind of a permutation is this?
It's alternating.
It's alternating. Why? Because this element is bigger than this, which is smaller than this, which is bigger than this. Okay, so it's
Yes.
an alternating, first of all, it's a zigzag. And then what kind of a zigzag was it? It was a down first. Therefore, it's an alternating permutation. Another example, if I just switch these in between two elements, 3, 4, 1, 2. So again, I have a this thing bigger than this, smaller than this, bigger than this. So this is also a zigzag, but this is a different kind of zigzag, right?
Not down first.
It's a up first and down later. First element is smaller than the second one. So this is actually corresponding to something of this type, right? For that permutation, the set of descents is the set 2, 4, because W2 is bigger than W3.
Yes.
Or 4 anyway doesn't come because you can't compare it with the next. Okay. So what is this type? We will see in a while, but few questions which we should keep in our mind are, so how many alternating permutations are there in a GN? For any n, Gn is there, the set of permutations. But out of all these permutations, how many permutations are alternating permutations? And given a alternating permutation, can you reverse such permutation? Like how we did here, or rather what we said here, that this was a down first, up later. So instead of this, if I had something, let's say, so isn't there a, okay. So if let's say I forget about this piece, okay, and I put a W1 here, okay, so then it's a sequence starting from W2. So now the new permutation which I'm dealing with is W2, W3, W4, W5, W6, W7, W8, W1. So this is also a zigzag. However, this is a zigzag of a different type in which you take a up first and down later, right? So you have in some sense reversed it.
But we cannot do this always, right? Like,
No, here I am giving you just an example.
okay.
So in by what I really mean by saying that, can I reverse something like this? So by reverse, I actually technically, if I want to be correct, what I'm saying is that instead of considering down first and up later sequence, can I consider down later, up first sequences? If so, then what? What do I get? What is special about them? Can I study them? And one such example of such a up first and down later sequence would be like this, that you would have forgotten about your W1, excuse me, and you would have started from W2 and appended W1 at the end and say that W1 was the largest element. Okay.
Yes, ma'am.
So in such a scenario, what would have happened? So what does an up, down, and okay, so sometimes to make it shorthand, down first, up later is simply said down up. And therefore the what I'm saying as up first, down later will be called up down. That is, you take up first and down later. So what does such a sequence give? And also, is every permutation of Gn is one of this type? These are the questions we will see now. So if you take W in Gn, then this is reverse alternating if this zigzag is satisfied. So W1 is less than W2, bigger than W3, less than W4, bigger than W5, and so on. Pictorially, I would have taken a up, then down, then up, then down, then up, then down, and so on. Okay. So what we defined earlier was alternating. What we're defining now is reverse alternating. So this is also a zigzag, but this zigzag is of the type up first and down later. So it's an up-down sequence. So such sequences correspond to reverse alternating permutations. Okay. So this is the caution which I was giving earlier, that what we have defined as the reverse alternating permutation is actually defined as alternating permutation in most of the books. So just be a little careful while you deal with these things so that you don't confuse yourself. Just cross check what is the definition of alternating for them and what is the definition for alternating for us, and then whatever results, if you are reading and trying to grasp, you should be able to understand them. Okay.
Yes, ma'am.
So moving forward, so remember the topic said descents, alternating permutations, and Euler number. So Euler number is what we will see next. Okay, so what was this? 3412? What kind of permutation is this?
Reverse alternating.
Reverse alternating, great. So another question which is there in our head is how many alternating permutations are there, or how many reverse alternating permutations are there? Okay. So for that, we move to the Euler number. So in Gn, Euler number is nothing but the count of permutations which are alternating. And we fix the number of 0 alternating permutations to be 1, which means when n is 0, you're working with empty set, the number of alternating permutations is 1. Also, if you see any set W in Gn is alternating, if and only if this is nothing but reversing the sequence, you consider n plus 1 and you subtract every element W1, W2 up to Wn from this number n plus 1. So then you said W1 was smaller than W2, right? Now, you have taken minus of W1 and minus of W2. So the inequality would reverse. So minus of W1 is larger than minus of W2. Right? Basic inequality.
Yes, ma'am.
And now in this, when you add your n plus 1 as a positive number, why n plus 1 to be precise, we'll see in a moment. We'll understand actually. But once you have got some a is bigger than b, now you add any positive number, q let's say, then a plus q remains bigger than b plus q.
Yes.
Adding positive numbers do not change the inequality at all.
Right.
Right? Therefore, and then W2 is less than, W2 is bigger than W3, but minus W2 will be smaller than minus W3.
Yes.
So minus of W2 then added with n plus 1 stays smaller than minus of W3 plus n plus 1. Right?
Yes, ma'am.
Yes.
So this way, when you keep continuing, you are actually reversing this particular zigzag. So W1, so the first element W1, which was smaller than W2, with manipulation, now the first element of the new sequence is actually larger than the second element. Correct?
Yes, ma'am.
And you have done this to each of these arrows. There were exactly n minus 1 arrows, and each of these arrows were in a zigzag pattern. If there was an up arrow, it was immediately followed by a down arrow. And similarly, every down arrow was immediately followed by a up arrow. So now each up arrow has been converted to a down arrow, and every down arrow has been converted to an up arrow. And this same technique you could have done even to an alternating zigzag. This was a reverse alternating zigzag where I explained this entire thing. But the same phenomenon you could have done here as well, correct?
Yes.
Correct. So some particular sequence of zigzags is alternating if and only if n plus 1 minus these numbers is reverse alternating, right? So to a negative of this entire thing, you add n plus 1, this becomes reverse alternating, and this becomes alternating, correct? So there's a bijection between alternating and reverse alternating permutations.
Yes.
Therefore, the Euler number, which you define to be the number of alternating permutations of Gn, also counts the number of reverse
Reverse
alternating permutations of the Gn. And that is a good news. Oh, ignore this. This is incorrect. Therefore, the number of, okay, this I've already said. Okay, now the exponential generating function for Euler number is this. So Euler number is En, okay? En is the notation. And you're taking exponential generating function, so there is an n factorial here. So summation En xn n by n factorial, summation running from n greater than equal to 0 is sec x plus tan x, which is 1 plus x squared by 2 and so on, blah, blah, blah. You know this. And few lectures back, we saw some Taylor series expansions, some famous expansions and some not so famous expansions. One of them was sec x also. So just to recall it back, sec x is 1 plus x squared by 2 plus 5x 4 by 4 factorial plus 61 x 6 by 6 factorial and so on. So clearly this has only even powers of x, right?
Yes.
X raised to 0, x raised to 2, x raised to 4, x raised to 6. Correct? So
Yes.
instead of sec x, if I had considered sec of minus x, what will be the answer?
Same thing.
So sec of minus x is equals to
Sec of x.
sec of x. Therefore, sec is an even function.
Oh.
It's an even function when the variable changed to negative of it does not change the value of the function.
Yes.
It's odd if it becomes negative. So if f of minus x is f of x, then it's an even function. If f of minus x is minus of fx, then it's an odd
Odd
function.
function.
Okay, so sec of minus x is turning out to be sec of x, therefore it's an even function. And this later part, the tan x, when you take the terms out, it's actually x, 2x cube over 3 factorial, 16x5 over 5 factorial, and so on, has only the odd powers, correct? So here, if I have put tan of minus x, I'm going to get a minus x, 2 times minus x whole cube, so a minus will come out here, 16 minus x whole raised to 5, so minus will come out here, and so on. So for this entire expression, there will be a minus of this entire thing inside with all the samans in plus. Okay, so tan of minus x is actually minus of tan x. Therefore, tan x is an odd function. Thus, this can be safely broken and written that summation e to n, which means collecting only the even terms, x raised to 2n over 2n factorial is sec x, and summation e to n plus 1 odd powers of x divided by 2n plus 1 factorial is actually the tan x. Okay. So all this is fine because since I started from n equals 0, I have taken 2n plus 1 here. If I would have started n from 1, because you might say, ma'am, since you have already taken a 0 here, why start from 0 in this? So if you were starting it with a 1 here, I would have put in a 2n minus 1 here. Okay, so that my x raised to 1 is also accounted for. Okay, so these are the reasons why e to n, the Euler number for the 2n. So remember, this is the number. Euler number En counts the number of alternating permutations in Gn. So when it is counting the number of alternating permutations in an even number set, it's called a secant number. E2n is called a secant number because E2n can be expressed as sec x. And for same reason, E2n plus 1x, E2n plus 1, which is the which is counting the number of alternating permutations in an odd cardinality set, is called a tangent number, because this can be expressed as a tan x. Okay, and these can be taken as definitions of sec x and tan x once you have done this theory. Okay.
Yes, ma'am.
So I had to cover permutations of multisets also, but my notes are not complete. So today's lecture I will stop here. And I want to discuss a little about the quiz. So what I have thought of, so all of you have internet at your home, right?
Yes.
Yes.
Because I do not plan to give a take-home exam as quiz. So what we will do is, I will generate different Google Meet links for all of you.
Okay.
Okay. So the quiz is starting at 12:30 p.m., right?
Yes.
So by 12:20 or so, you would get a Google Meet link. Okay, each of you will get a distinct Google Meet link, and you have to come to that Google Meet link. I will share quiz with each of you individually. Okay, so there
Okay.
can be different questions, there can be same questions, and either in one shot I will give you all the questions, or I will give one question and give you a 5-minute window. You handwrite your solution, take a like take a scan or take a snapshot of your notebook and send it back to the Google Meet link itself. Okay. Or
Okay.
email me, whichever way you find comfortable, and you have to keep your video on. So no excuses like, ma'am, I'm not in a presentable form right now, so I can't turn on my video. That won't work. So keep yourself prepared for this sort of
Can we send the pictures over WhatsApp to you?
Yeah, that is also fine. I can
Yes, ma'am.
transfer them
That
to
is
my
easier
email.
actually.
Huh?
That is actually easier.
Whichever,
And it's
that is
quicker. Yeah.
up to you.
And if you want, after the exam is, I mean, after we have sent you in WhatsApp, we can compile it to a single PDF and send it afterwards also.
Yeah.
That is okay. That is okay. Because as I told, I am not planning to keep quiz to be very much hardcore theoretical, to be precise. So there won't be, I mean, you will have to think more, but write less.
Okay.
Okay. So
And what will be the total duration of the quiz?
30 minutes.
Okay.
Okay.
30 minutes quiz. Syllabus I've already told. And
So we should join by 12:20, correct?
yeah, you will get a link from me, and only after that you can join, right?
Yes, ma'am. So by 12:20 or 12:30.
Yeah. I should be providing the links by 12:15 and you join. I mean, then you can
Okay.
join as per your convenience time, but latest by 12:28, you should be in the meeting.
Yeah, okay.
Because if I am keeping it so time restricted, then if you are joining late, you are going to lose time. Okay.
Okay, ma'am. Yeah.
Okay, got it.
And since this would happen like over individual windows, I don't know if Saham would join or not. And there is one more student who should be giving this exam. So I would suggest either you can be prepared with some A4 sheets and on each sheet, each side, you keep your name written.
Okay.
Okay.
Because I do not know any of yours handwriting, no? So I will not be able to recognize who has written what later. Otherwise, I'll have to keep cross-checking it with what you have, who sent what. And this way I would just print it out and grade it. And I mean, as per your names, I'll just sort the pages and send it back to you. Okay.
Yes, ma'am.
So since at that time, it would be hard for you to remember this, that you have to put in your names. People even forget to put their roll numbers in exams like JEE and all. So keep these pages prepared. Okay.
So only name, right? Not roll numbers and all are not needed.
One thing is sufficient, like your
Okay.
identity should come to me either
Yeah,
through
okay.
your name, through your roll number, whichever way you find appropriate or
Okay.
easy. Like at least one thing, because I can then identify you,
Yes, got it.
so that then it'll be easy for me to compile the pages at the end. Okay, preferably same thing, one question on one page. So even if it's a 2-page answer, please change the page.
Okay.
Okay. So yeah, this is all that I have to say for now. And yeah, guys, please read inversions, because otherwise, I mean, already I am also lacking. I had promised to deliver one more lecture in this weekend, which I didn't. And this coming week is your quiz. So let's see. Anyway, we have to finish this. So that would happen. No doubts about that. But let's try to keep ourselves more motivated. Okay.
Yes. Mhm.
Okay. If you have anything else to ask now, we still have some time.
No, ma'am.
Okay. So this information about this quiz, I will just put in the, or I don't know, do you people know each other? Like, have you people even met? Since for 2 years we are online.
No, ma'am.
We
Like I
haven't
am.
met physically.
No, ma'am. I haven't also.
So you might not have even seen CMI, no?
Right.
No, ma'am. Yeah, I didn't.
I didn't either.
Oh, then who was that person who was sitting in the library that day?
Oh, there he had left the class, I think. He is not continuing.
What was that person's name?
Deepak, most probably.
No, not Deepak. Deepak, I know. I taught him last semester also.
Oh,
It was some other person. Okay, never mind. Doesn't matter. So, ठीक है. Then possibly you don't know Saham also, no?
no.
No,
And
ma'am.
anyone knows Nirankush?
No.
No, ma'am.
Uh,
I can maybe talk to them. That's not a problem. I can convey this.
Yeah, we are in the WhatsApp group. So
yeah,
Yeah, we can.
I mean, Saham is there. Nirankush is not there. And Nirankush is also part of this course.
who is I mean, did he attend these lectures? I don't
No, he
remember.
hasn't attended any of the lectures so far. He submitted the assignment.
Okay.
So, I mean, since he's not attending the lectures, it is hard to convey any of such messages also to him.
There is one more person in the WhatsApp group.
Yeah, who is that fellow?
I don't know. He
Let me see.
Rishi. It says the name is Rishi, but
Who would be Rishikesh then?
okay.
Okay. So I have messaged him. We'll see if he is attending or not. Saham is easy to inform. This other fellow is, I don't know how to inform him. And this much information I do not want to put out on Moodle. So, okay, let's see. Maybe I'll email him. Okay, see you guys.
Okay, bye,
Day
ma'am.
after tomorrow.
Yeah.
Okay.